So, all right, everybody get out their calculators. Oh, they don't want credit. They didn't do that for the credit, they did it for the joy of learning. Oh, I'll give them credit anyway. I'm that kind of guy. All right, so, calculator's out. Anybody doesn't have a calculator, so I can push buttons. So I need you pushing buttons with me today. Anybody without a calculator? Okay, first thing I need to do is look at the top of your calculator. Who has a calculator that says multi-view at the top? If you've got a multi-view calculator, your issue is going to be order of operations, okay? So that your calculator does not write scientific notation as a number, it writes it as a math problem. So when order of operations matter, which means in subtraction and division, remember that it matters in subtraction and division, because addition and multiplication are commutative. So it doesn't matter which order you do them. But in subtraction and division, you actually have to make sure that you put them in parentheses. You actually have to take the time to write the parentheses. That's the difference you have to do with the multi-view, is you got to put the scientific notation in parentheses. Okay, so I asked you to get a calculator with a specific button on it. So everybody find that button on your calculator. It's not the one that says 10 to the x. Okay? That's the one that's above log. You don't want that one. You want EE, which is often on the button above 7 on TIs, either regular or shifted. Could be at the bottom center. If you got a Casio, it actually says times 10 to the x in the bottom center. That's okay. Okay. Sometimes it's a shifted key. Is everybody able to find that button on their calculator? Find that button on their calculator. Everybody find it? Anybody not find it? Let me help you use your calculator. Hey, that's my goal today, is to help you use your calculator. So yours is, it's on here someplace. What's it? Yeah, so you're going to have to use the x to the n, but you're going to use parentheses around it, okay? Anybody else? Yeah, yours is right here, EXP right here. Okay. Yeah. Find the button. Make sure we all got the same button. Yours is the time 10 to the x in the bottom. Yours is this one right here. Okay. Anybody else? Yours with the multi-view, it is, ooh, you got a bizarre one. Oh, it's this one right here. Okay, anybody else? Yeah. And remember, you're going to have to use it with, there it is right there. And you're going to have to put parentheses around it. Okay. Everybody got it? Anybody not able to find their button? Yep, and it's shifted, so you can push shift before you hit it, okay? All right, so we all found the magic button. So now let's say we wanted to get 4.5 times 10 to the negative fourth into our calculator. Follow along with me as we get it into our calculator. Push 4.5. So first you put the number part of it. Then you stop, and the next thing you push is the magic button. You don't push times, you don't push 10, you just push that button. Your screen is going to change in some way. Some calculators write times 10 to the x. Some calculators put a couple of numbers in the upper right-hand corner. Some calculators take the number that you had, shift it over, and leave two numbers. Some calculators put the letter E down there to tell you the next one's an exponent of 10. So anybody's calculator screen I have not described yet. I did the most common ones. There's some other ones out there. Those are the most common ones. I have to know how to run all of the calculators. Okay. So now, when you push that button, it took place at the times, it took place at the 10, and it took place at the to the. So the next thing you do is enter an exponent. So my exponent has got to be negative 4. So not subtraction 4, negative. You've got to change sign one versus, you said negative in parentheses or a plus minus button, and then the 4. Okay? That's how, if you look at your screen before you push equals, that's how your calculator is going to write 4.5 times 10 to the negative fourth. Okay? You're going to have to translate between your screen and your paper, because many calculators don't write the times 10 to for you. You've got to take the time and write that out. Okay. So you push that plus or minus and get the 4 and see what your display says. That's how your calculator is going to write it. Now, okay, so then you pushed a button wrong someplace. Let's go see where you did. Well, let me go backwards. There. Oh, somehow you have an arrow in there. So it's -4. Okay, now push the equals button. For some of you, it'll leave it the way it was. For others, it will write 0.00045. Why would it write that? That's 4.5 times 10 to the -4th. Okay? Remember, all we're doing is trying to write a number differently so we can get it into our calculator easily. Okay? So the button stands for the times. It stands to the So you enter number, button, next number. Nothing in between. Right, let me check to see. Okay. Let's see what this is. Oh, you put an exponent here. This doesn't need to be an exponent. Where's your delete? Delete. Okay, so 4.5 exp -4.
Oh, that's it?
That's it.
Oh, okay.
Yeah, the button does a lot of the work.
Oh, okay.
And then, yeah, change button. Okay, so the work. Okay, so the button takes care of most of the work for you. Type number, hit the button, type another number. People want to put those tens in there and those times in there. You don't want those; it'll mess you up. Okay. So let's try a few math problems because 59 and 60 are going to have you do math problems in scientific notation. So 6.0 times 10 to the third times 3.8 times 10 to the second. So push along with me. 6.0 magic button 3 times 3.8 magic button 2 equals. And if you've pushed buttons successfully, your calculator will say 2,280,000, or it might say 2.28 times 10 to the 6th, depending on your calculator. Is there anybody who did not get one of those two numbers when you push those buttons? Anybody who got something else? Because now's the time to fix it. You want to fix it here so that you don't make the same mistake at home. Everybody okay? Everybody got this? Everybody know this is the wrong answer? Why is it wrong? So we did math. We need to think about sig figs. How many sig figs in 6.0 times 10 to the second, or 10 to the third? 2. How many in 3.8 times 10 to the second? 2. So how many should be in my answer? 2. So this should be 2,300,000, or 2.3 times 10 to the 6th. Make sense? Because every time you do math from this point forward, I expect you to do sig figs. That's how you get good at them, is doing them every time you do math. Okay? All right. So let's take those same numbers, or almost the same numbers, and subtract them. So you push the buttons on your calculator. 6.08 times 10 to the third minus 3.2 times 10 to the second equals, if you have successfully pushed buttons, you will get 5,760. Okay. Anybody not able to get 5,760 to show up on their calculator? And for those using the multi-view, this is where you got to make sure, put in parentheses. Okay. So, sig figs. What math operation is it? Subtraction. So since it's subtraction, I have to line up decimal points. Well, looking at this, Whoa, whoa. Let's go a little bit more basic. How is 6 minus 3 5? Doesn't that say 6 minus 3 and the first digit's a 5? How the heck is that possible? Because the 6 and the 3 are not in the same place. These have different exponents, so the decimal point's not in the same place for both of those. So scientific notation, when you're doing the sig figs or scientific notation, you have to stop and write it down. Okay, so 6.08 times 10 to the third minus 3.2 times 10 to the second. I can't subtract those two because they're not to the same power of 10. So I have to make them the same power of 10. It doesn't matter which one I choose. I usually make the small one bigger. It tends to work more often. I got fewer changes that way. It doesn't actually matter which one you do. There might be an extra step at the end if you pick the wrong one to get it back to standard form. It'll be the right answer, just to be in the wrong format. Okay, so I'm going to change that exponent. I'm going to change that 2 into a 3. I made the exponent bigger, so I have to make the number smaller. So it's not going to be 3.2, it's going to be 0.32. And now, when I subtract, I get 6, 7, 5.76. Now there's where the 5 came from. And I keep the 10 to the third. But that tells me where my decimal point really is. I do it longhand because now I can do sig figs. Right, now I can do sig figs. These both have 2 decimal places. So my answer's got to be where that 6 is at. So that 6 is significant. In 5,760, that 6 is significant, the 0 is not. So this is the correct answer as well as that. Those are both the right number of sig figs after I did the subtraction because they line up. Here's what people tend to do. They say, oh, 6.08 has 3, 3.2 has 2, I'm going to have 2 in my answer. Because that's the multiplication rules. Don't use multiplication rules when we're doing subtraction. I told you like the multiplication rules better and you want to use them all over the place. Just got to remember they don't work for adding and subtracting. Okay? Hey, another subtraction problem. So you push the buttons on your calculator, 6.08, EE negative 2, minus 3.2, EE negative 3, equals, now that equaled 0.0576, or 5.76 times 10 to the minus second. Anybody not able to get that on your calculator? Anybody? Let me help you. Okay, why the 576 again? Because I had to do that same trick. The negative 2 and the negative 3 are not the same size. So I turned the negative 3 into a negative 2. From negative 3 to negative 2, I made it bigger, so I need to make the number smaller. I'm at 0.32. And the only difference is now it's negative 2 instead of to the third power. They still line up the same way. Now, we could have done this the long way. 6.0608 minus 0.0032. That gives me 0.0576. Right? We could have done it the long, taken it out of scientific notation, done the subtraction. We would have got the same answer. Sig figs would have been in the same place. Right? But we need to do it without taking it out of scientific notation because of problems like this. You don't want to do this one by taking it out of the scientific notation because you really don't like writing 18 zeros for the first one and 19 zeros for the second one. And then trying to make them all line up. So you push buttons on your calculator. 5.33 times 10 to the 20th minus 3.8 times 10 to the 21st equals, and if you have successfully pushed buttons, you will get negative 3.267 times 10 to the 21st. Why is this negative? Yeah, the second number is bigger than the first number. 10 to the 21st is bigger than 10 to the 20th. So if I take a bigger number from a smaller number, I get a negative number. Right? Okay, now I'm going to think about rounding. Where do you round it? Well, I have to write it out. 5.33 times 10 to the 20th minus 3.8 times 10 to the 21st. I usually make the big one smaller, and I usually make the 20 into a 21, but I want to show you that it works the other way too. So I'm going to make the big one smaller instead this time. So I made the 21 into a 20. Okay? Well, I made the exponent smaller, so I have to make the number bigger. So it's not 3.8, it's 38. And 5.33 minus 38 is 7, 6, that's a 7, 2, 32.67 times 10 to the 20th. And I needed to do that so I could round off in the right place. The right place is where the 2 is at. Everybody see the 2 is an estimate? The 6 and the 7 I have no idea about. So that makes it really 33 times 10 to the 20th, but 33 is not between 1 and 10. So I get 3.3 times 10 to the 21st. So that's the added step if you change the wrong one. You just got to go one more step to get it back to standard form, because that first number has to be between 1 and 10. That's the worst thing that could happen, is you could choose the wrong one to change, and you have to go one step more. With addition, you could add up to a number bigger than 10, and then you have to add a 10 to get it in scientific notation. Get that first number between 1 and 10. Okay? Make sense? Horrible? Okay. Calculator practice 9 on 59 and 60. The rest of the day is going to be about the metric system. Hey. It's officially called Le Système International by the French, because the French came up with it. The metric system came out of the French Revolution. Okay? They wanted a new system of measurement because they wanted to get rid of everything that was connected to the king. Everything connected to monarchy, they hated monarchy. If it was connected to monarchy, they got rid of it. They wanted to build everything based on nature. So they came up with a new measuring system that was completely built on nature. Okay? Because the old system had a couple of problems. Here's one of them. Back then, how long was a foot? It was the size of the king's foot. So when you got a new king, you got a new foot. And you went from one country to another, the foot changed size. Is that going to make business easy? No. Hey, that's a big problem with it, right? So, hey. So they came up with another one. They didn't want to use the king's foot, so they found things that were based on nature, okay, and off each other. They wanted to define as few as possible and then build off of those. Okay, so we've been focused on the numbers for the past couple of days, but numbers are only half of a measurement. Let me show you why I mean numbers are only half of a measurement. Okay, I picked something up yesterday and it was 10 long. Try to draw a picture of it. Do you have any information for drawing a picture of it? Do you have any pictures in your head how big it is? All you know is it's bigger than 9 and smaller than 11. But you have no idea how big it is, right? So, because I need a unit there. So numbers without units are meaningless. And how do teachers mark meaningless answers? Meaningless answers are wrong. You have to include the units every time. Without a unit, it doesn't have any meaning. You'll watch. I've been doing this for 30 years. No, I started when I was in high school. I had to write the units every time. You'll find that units are your friends. They actually help you solve the problem. Okay? Units are good things. In the past, you did it because your teacher told you to. I'm going to show you they're going to help you set up the problem and get the right answer. They're your friends. Okay, so we had one problem that was tied to the king. Here's another problem. How many feet are in a yard? Most people want to say 3. There's a second answer. It depends on how many people are standing in it. True. Okay. So it's 3, right? How many feet are in a mile? Fewer people know this, but track people tend to know it's 5,280 because they get to run around lots of time. 1,600? Oh, you go into meters? Oh, good. Because if you want to compete internationally, you got to be meters. Oh, sweet. Good. Cross country's still in miles, though. So it's 5Ks? Wow, good. I love it that they went to metric. Join the rest of the world. Okay, because the rest of the world uses metric system. There are 3 countries in the world that don't. The United States, Liberia, and Myanmar, formerly known as Burma. And Myanmar's changing. Soon to be 2. We're making it expensive on ourselves for not doing it. Okay, how many feet are in a rod? It's in our system. Is the rod? Anybody know how far it is? How about the chain? Okay, a rod is 16 and a half feet. Everybody knows a rod is 16 and a half feet. Okay, say, why are you talking about it? Oh, first of all, those are bizarre numbers, right? Do you want to do numbers? Do you want to do math in your head with numbers like 3, 5,280, and 16 and a half? Those are the kind of numbers you can do math in your head with? No. So converting is a pain in the English system. Okay? Metric system gets rid of that. It makes converting easily. Okay? The metric system is easier to use because it's a decimal system. That means every conversion is some power of 10. And we like things that are powers of 10 because 10 is the third easiest number to do math with after 0 and 1. Because doing math with 10s is just moving a decimal point, right? So every conversion is going to be some power of 10, so we'll be able to do it in our head. Okay. Talked to history about this, said France was the first country to go metric. They came up with it. Who was second? Who was the second country to go metric, agree to go metric? The United States. When Thomas Jefferson was the Secretary of State for George Washington, he signed a treaty with France that said the United States would go metric. Because they figured we didn't like the king either. Because we kicked him out first with their help. Right? The United States agreed to go metric. We haven't got there yet. Kind of slow. Here's proof of it. The United States was the first country to have decimal money. First country to have a decimal point in their money. Up to that, it was all about changing coins. How many pennies in a shilling? Or if your penny was too much, you literally cut it in half and gave them a halfpenny, half a penny. Because everything was based on coins, whole chunks. That's how money worked until the United States came up with the decimal point. Pretty good idea, I think. Okay? Such a good idea but the stock exchange didn't start going to decimal points until about 15 years ago. They were doing fractions when I was growing up. It was so much and a fraction, not and a decimal point. It took the stock exchange a long time to get to decimal points. Okay, a metric unit is going to have 2 parts. Well, it can have up to 2 parts. It will always have a base unit. It might have a prefix. You've studied the metric system during science class before, I'm assuming. Right? You do this every year. Okay. Well, we need to live it because these are the units we're going to be working with all the time. Scientists work in the metric system. Now, track's all metric now. Is the pool gone metric yet? Any swimmers here? Has the pool gone metric?
Yeah.
All right. Yeah, you wish it was 400 yards, not 400 meters, right? Okay. Meters are a little longer. Okay. The prefix tells you how many times or multiply or divide by 10. So you're going to have a base unit, and you're either going to have 10 times that base unit or 1/10 that base unit, 100 times that base unit or 1/100th of that base unit. But I can do those kinds of numbers in my head. I like those kinds of numbers. I can do that in my head. I do not want to do 16 and a half in my head. Okay. So we're going to have a base unit, something one size, and then we're going to put prefixes on the front if we want to modify it. And the prefixes are all the same. We only have to learn one set of prefixes, and it works for everything. Which isn't true in English. 12 inches to a foot, but how many ounces to a pound? 16 ounces to a pound. So as you go from one kind of measurement to another, the conversions all change. It's a pain. English system is messed up. Everybody agreed? I'm pointing out its flaws, aren't I? Okay. Base unit of length is the meter. This is a meter. It's meter stick. Okay. If you flip it over, it's not a yardstick because a yard is right here. So you got this much more than a yard. About 10% more than a yard. It's about 3 inches longer than a yard. So the 400 meters about 10% further than the 400 yards. Okay. And the little m is the abbreviation for meter. Original definition was 1/10,000,000th the distance from the North Pole to the equator. Through Paris, France. Had to go through Paris, France. Now it's defined as so many wavelengths of an orange red light. We'll see why that's the distance measurement a little bit later this year. Okay, mass. Mass is measured in grams. And a gram is a little amount of stuff. It's about how heavy a raisin or a paper clip would be. So a gram is a small amount of weight. Its symbol, lowercase g. Time. Base unit of time is the second. Time is the one place where we're not metric, because we do seconds, minutes, and hours. That's Babylonian math. They tried to go, the French made a metric clock. They put a clock up that had 10, divided the day into 10 even pieces. And each one of those tenths of a day was cut into 10 even pieces. Each one of those 10 even pieces was cut into another 10 even pieces. And they built a clock that worked that way. And you could tell exactly what time it was by looking at it in metric time. And when you were at 5, you were halfway. When you were at 0.5, you were halfway through the day. Okay? So you know how far you were through the day. Okay? So noon would have been 0.5. Midnight would have been 0. Okay? That's how the clock worked. But nobody looked at that clock because right next to it was the church clock that had the old system. So nobody bothered to look at the metric clock. Everybody looked at the church clocks. So they stuck with the second as the big unit of time. So we get to do Babylonian math and do math in 60s. Because Babylon did their math in base 60. Which is kind of strange. Temperature. Temperature is measured in 2 different units. The real one is Kelvin, but people don't use that because it's inconvenient. Gives you big numbers that don't really give you a sense of scale. So more often they use degrees Celsius. You may notice that these are capitalized. They're capitalized because they're named after a person. There was a Kelvin, there was a Celsius. Second thing you'll notice is that Celsius gets a degree sign and Kelvin doesn't. We'll talk about why that is later. Okay? Kelvin doesn't get a degree sign, either in the symbol or in the thing. Okay, energy is joules, named after Robert Joule, guy who studied all this energy stuff in the 1800s. So it's a capital J. Volume is the liter. And a liter is about half the size of a 2-liter bottle. It's strange, the one place we really did go metric was soda. Actually, it was soda and liquor. Liquor's all metric now, too. Okay. Now, this is a capitalized L, but it's not because there was a Mr. Liter. It's because of typewriters. Okay. When they're doing this, they're making typewriters. And on a typewriter, this is a 1. This is a lowercase l. So if you saw this, could you see how you could mistake that for 211 instead of 21 liters? That's why they use a capital L. It's because you're not going to make that mistake. It's about typewriters. Okay. The amount of substance is the mole. Now, you probably never used mole before. There's other ones you may have heard of before. You probably never heard of mole and never used it before, because mole is one that's used mostly for chemistry. We will use mole a lot. And strange, it's got the shortest name, but it's got the longest abbreviation. That is the official abbreviation, MOL. You leave off the E. Okay. So those are the base units. And we're going to take those base units and multiply or divide them by 10. So there are lots of prefixes. I'm not going to teach you all the prefixes. If you need to know them, they're in your textbook. Okay. The only prefix that we're going to learn that's bigger than the base unit is kilo. Kilo's symbol is a lowercase k, and it means 1,000 times bigger. It's the only one that's bigger than the base unit. So this is a meter. A kilometer would be 1,000 of these laid end to end. It's going to be a big distance. A gram is a raisin. A kilogram is a box of raisins, a big box of raisins, 1,000 raisins in the ballpark. Make sense? Okay, it's the only one that's bigger. Then we're going to learn some that are smaller. It's the only one we need that's bigger. There's also deca and hecta in there, but we're not going to use those. Okay. Then deci from decimal. Move the decimal points, you've moved by 1/10. That one, that's not a big surprise that deci means 1/10. Okay. Here's one that we use all the time, and it's tied to that money thing. Centi means 1/100th. This is the one that everybody should be able to remember easily. So, why should I be able to remember it easily? Okay. What do you call 1/100th of a dollar? A cent. We have decimal money? Okay. How many years are there in a century? 100. Okay. Okay. Little c means cent. Okay, next one's smaller. Keep getting smaller. Instead of 100th, 1,000th is milli. Lowercase m. So, oh, we got a problem here. We said meter was lowercase m. Milli is also lowercase m. So if I see a lowercase m by itself, which one is it? Well, am I going to have milli without something after it? No. So by itself, it's got to be meter. If it's leading at something else, then it'll be milli. Okay, 1/1000. So the individual little lines on this, every line's a millimeter. Okay. Now, if you took the space for one of those lines and you cut it into 1,000 lines, you made as many lines in between as there are in this whole thing. Each one of those lines would be a micrometer. 1/1,000,000th of a meter. Micro means small. Microscope. Scope for view. Micro, small. Viewing small things. Microscope. Okay, now, got an M problem again. I can't use M for micro. So, because I already used it for milli and for meter, so I can't use it for micro. I can't use capital M because capital M is mega, one of the big prefixes we're not learning. So they had to find something to take its place, so they chose this, which is the Greek letter mu. We're going to learn some Greek alphabet this year because we're going to run out of letters. Okay, it's the Greek letter mu. Eventually, this mu became our M when the lines started getting about the same size. Over time, it evolved into an M. That's where our M came out of the mu as technology for writing, because the Greeks chiseled it in stone and wrote it with feathers. Okay. So as the technology changed, the way you wrote the letters changed. Okay. So micro is small. But if you take one of those micrometers and cut it into 1,000 pieces, then you'd have a nanometer. Nano, symbol N, means 1/100000th. So we said the millimeter is about the size of a wire hair. Okay, microscope, you see individual cells in a microscope. You see all the parts of a cell. Okay, that's what happens when you get down. So you're seeing things on the scale of millionth. When you get down to nanometers, you're talking about individual atoms. That a nanometer is a few atoms across. So when they talk about nanotechnology means they're building materials and equipment at the nanometer scale. That they're building an electric motor that's 100 nanometers across, which is 1/10,000,000th of a meter. Okay. So nanotechnology, they're manipulating individual atoms to put them in exactly the spot they want them to be to have a certain set of properties. They found that if silver atoms, bacteria can't hang on to silver atoms. So in plastics, a few plastics, they're embedding silver atoms every so far apart in the plastic. They're just far apart enough that there's no place that a microbe can land that it doesn't hit a silver atom. So you'll never see the silver in it because it's just individual atoms spaced across the surface. Okay? Because they can't hang on if there's silver there. So they just make them sure they're the right space apart so that you're always going to hit one. Okay? So, and here's how they get used. The ones we use to measure meters most often would be kilometer. A kilometer is about 6/10 of a mile. Yeah, I found this out when I was driving across Canada this summer. Down in Canada, got on the freeway, and here comes the sign. Speed limit, 120 kilometers an hour. It's about 75 miles an hour. But speed limit said 120. I can go 120. Okay, but we use kilometers where we use miles. Centimeter. The individual numbers cut up on here, those are centimeters. There'd be 100 of them. If I cut this into 100 pieces, each one would be a little bit bigger than half an inch. Well, it's a little bit smaller than half an inch, sorry. They use centimeters the way we use inches. Yeah. Millimeter. A millimeter would be the individual lines on here, and that's about the width of a wire on a paperclip. Not the whole paperclip, just the wire on the paperclip is about a millimeter. So you use that for measuring really small distances. Your socket wrenches and stuff are in millimeters. Because you would not want a 10 centimeter socket wrench because the nut would be this big. Okay. Okay. So, volume. You know, volume can be calculated by multiplying length times width times height. Right? Because volume is measured two ways. Volume is measured in a measuring cup, or you can measure it with a ruler doing length times width times height. So it's got two different views of volume. There's ones where it's got cubes and ones that just have gallons. We got gallons and we got cubic inches. Well, the metric system has liters, and then they're going to have one based on this. Okay? And here's what a liter is. This is a liter. A liter is a cube, 1 decimeter on a side. Okay? As you read through, hopefully everybody got the big point about why we don't use cubic meters. Because a cubic meter would be this wide, by this tall, by that deep. Okay? And if I ask you to go to the store, you're going to stop by the store after school today, how many cubic meters of soda are you going to buy? See, that's what they mean by it's not practical or convenient. It's just too big. Okay? Now, a decimeter, one-tenth of a meter, is going to be 10 centimeters. Because that's a hundredth of a meter. So 10 hundredths is the same as 1/10. So each one of these lines on here is a centimeter. And see how they make little cubes? Let's figure out how big those cubes are. So a liter is 1 decimeter cubed, or 1 cubic decimeter, depending on which way you want to say it. So a liter is 10 centimeters times 10 centimeters times 10 centimeters, length times width times height. That's going to be the size of this block. Everybody in agreement? 10 times 10 times 10 is 1,000. 10 times 10 is 100, times 10 more is 1,000. And centimeters times centimeters times centimeters is centimeters cubed. So a liter is 1,000 centimeters cubed, 1,000 cubic centimeters. If I were to, this block right here, if I were to cut it along those lines, I would get 1,000 little blocks. Each one would be a centimeter cubed. Because I've got cut across the face, I'll have 10 wide by 10 across, that's 100 on the face, and then I'd have 10 layers of those. There's my 1,000 little blocks. Okay, now I'm going to do a fancy piece of algebra. Don't get confused. Is 1/1000th of a liter 1 centimeter cubed? Yeah, see the complicated math I did there? Divide both sides by 1,000. Okay, that's okay to do, isn't it, right? But that seems like a lot to write. I have a shorter way of writing 1/1000th. We have a prefix that means 1/1000th. What prefix was it? Milli. So a milliliter and a cubic centimeter are exactly the same size. There's no difference in size between a milliliter and a cubic centimeter. So each one of the little corners on this block, this corner, is a milliliter and it's a cubic centimeter. Okay? So I found this was strange when I was looking at my brother. I was at my parents' house and my brother-in-law drove his motorcycle. He had a new Harley. And his Harley was a 1800cc big block Harley. my parents' car was a 1.3 liter Honda Escort. Or Ford Escort. Said, oh, 1,800 cubic centimeters. Well, 1,800 cubic centimeters would be 1,800 milliliters, which would be 1.8 liters. I said, whoa, my brother-in-law's motorcycle engine is bigger than the engine in my parents' car. But they don't look bigger. What the heck is that number? Well, that number is actually how much space is in the cylinder. Okay, because the power of a motorcycle explodes and it pushes the cylinder down. That space is how much space there is for it to expand in the cylinder. That's what it is. Because the more you can expand, the more power you can get out of it. Okay. So, volume is measured two ways, and we need to know this little factoid so we can connect the ones measured with the ruler to the ones measured with a graduated cylinder. And that's our connection, that 1 milliliter is 1 centimeter cubed. We look at that? Okay. So tonight's homework is going to ask you about the parts of the metric system. It's going to ask you to try to picture. So picture that prefix applied. What would it look like if it was cut into 1,000 pieces? What would it look like if it was multiplied 1,000 times bigger? Does that make sense? Picture a kiloliter. Yeah. 42. Oh, that's the answer to life, the universe, and everything. Get it? He's a cruel fruit. He really knows where his towel's at. What? Unless you're experienced, because then you know that the guy next to you will have a towel. And you can use his. Oh, all right, so making sense so far? So the 2 through 36 is going to be, there's going to be some percent error calculations, because we practiced those yesterday, right? Remember, if you change rules, you got to change and round. You got to round off and then change rules. Okay? There's a few metric questions, and then there's some practice using your calculator and doing scientific notation, which is where we should be. Okay? All right. So that is the day.